The light version of the quantum mechanics is called valence bond theory, in which a bond is formed by the overlap of atomic orbitals. So here we have sigma type overlap here. This is two p orbitals. Each p orbital is like this figure 8. And then we could also have pi type overlap. And so let me draw that here. You know, if we had a choice between overlapping one 3p orbital here and one 3p orbital here. Does this look familiar, or is this from the morning class? This is chapter 12 still. But where did I leave off on chapter 12? I can't. Did I talk about this? The bond? Yeah. All right. So this is a sigma type overlap. When we look at the internuclear axis, the overlap is within the internuclear axis. This is a pi type overlap here. Oops, let me get rid. I don't know why I did that. Here. When I draw the internuclear axis here, the overlap is above and below the internuclear axis. But when we compare sigma versus pi, sigma is going to form a stronger bond than a pi. So the two nuclei are going to be drawn directly towards each other. This one's going to go up and down. And that effect is the same. So when I look at fluorine, fluorine can gain an octet by sharing electrons here. And it shares it in this valence bond picture, which is overlapping p orbitals here. The two lobes here represent one p orbital, one of the two p orbitals, and the other two lobes represent another 2p orbital. And so I think I X this out because this fluorine is going to form a sigma type bond, not a pi type bond here, is what's observed here. Did we look at different levels of polarity here? The least polar would be fluorine versus fluorine, what we just looked at. Neither fluorine is going to win. They're going to have to share in order to get an octet. Whereas here, fluorine versus cesium. Cesium has an electronegativity of 0.8, fluorine's 4.0. And so there's a significant difference in strength. In fact, fluorine's strong enough to just pull that electron off. So cesium lost its valence electron, giving it a positive charge. Fluorine's gained that valence electron, giving it a negative charge, and an octet here. Cesium still has the full shell configuration as well. However, versus hydrogen, hydrogen has an electronegativity of 2.2, considerably stronger than cesium, but not as strong as fluorine, 4.0. And so there's going to be some uneven sharing. This is going to be biased towards fluorine, that is. Fluorine will have more of the electron cloud density than cesium, or excuse me, than hydrogen. And so we have different levels of polarity. Here we have a full dipole, that is a positive and a negative charge, positive and negative. Here we have, in the polar covalent case, we have partial charges. And so the electron hasn't completely been stripped off, but it results in a partial positive charge here and a partial negative charge here. This symbol, do you know what this symbol is called? This kind of S symbol here? Partial is what it means, but it's called delta. And so we end up with a delta plus and a delta minus. And so that's some polarity there, but the polarity is not going to be as big. You know, this will be lower polarity than this. Then when we go up here, there's no skewing of the electron cloud, and it's evenly shared. So we end up with zero charge here and zero charge here, and that's what we call nonpolar. There's no separation of charge. Did I talk about delta En? Uh-huh.
I think you already finished this.
I already did? Okay, good. This kind of looks familiar, right? All right. All right, then let's move on to chapter 13. Chapter 13 is going to be on the test as well. Okay, maybe I'll just do the lazy person's approach. Chapter 13 is a continuation of Lewis structures, and in addition to Lewis structures, we're going to be looking at the shapes of molecules. But the first part of chapter 13, let's just concentrate on the Lewis structures. So we're going to get some practice drawing Lewis structures first. And so the first thing is draw the Lewis structure for ammonia. Now, the procedure, there's certain steps in the procedure. The first step of the procedure is to sum up the valence electrons. So in ammonia, nitrogen has 5 valence electrons, hydrogen has 1, so that gives us a total of 8 valence electrons. And then we come up with some kind of skeleton, and then we fill in the electrons here. And so I'm going to do this. Actually, let me do this. Did we already do this, ammonia? Okay, do this, or NH3. Was that one of the ones here? Yeah, oh well. Okay, so I'm going to get a blank. From chapter 13. Okay, let me save this as. All right, so what we're going to do is we're going to go through the steps of generating Lewis structure here. And there are more things that we can do to do this here. So I'm going to do it a little bit differently than in the PowerPoint. And so the first structure that we want to do is NH3 here. And step one in drawing out Lewis structures is to total up the valence electrons. Sometimes we could skip this if you have some other ways of doing this, but if you don't, then just go ahead and do it this way. How many valence electrons does nitrogen have? Well, you look at what group number. What group number is it? Group number 15 or group 5? If it's group 5, then it has 5 valence electrons. And then we have 3 hydrogens, and hydrogen will be how many valence electrons? 1. And so altogether, I'm going to sum this up. I'm going to get a total of 8 valence electrons. Okay, that's step 1. In step 2, we want to build a skeleton, some kind of framework. And there are certain rules that, these rules aren't set in stone. These aren't necessarily laws, and sometimes we break the rules. Just be aware of that. But one of the rules is that hydrogen and fluorine are terminal. Only. Another way of saying this is they only form one bond. They only form one bond. And so what we aren't going to see is we aren't going to see things like this, where you're going to have a chain of hydrogen atoms. Something like this just isn't going to happen. We could see 2. For example, H2 is like this, but each hydrogen only has one bond. And the same thing, we could see F2, like we were just looking at. And when we generate F2, there's only one bond. But there's no series of F atoms strung together in a row like this. This doesn't happen. And so what that means is this. We have to put the nitrogen in the center, and then the hydrogens have to be attached to that. And so we end up with this. So when we build up a skeleton framework, what we do is we attach everything with single bonds like this. The single bond is just one line, and that line represents 2 electrons, in sharing the electrons. One electron from hydrogen, the other from nitrogen. And so how many electrons do we have here? We're supposed to have 8 electrons. In the structure, how many electrons do we have? Now, each line counts as 2 electrons, so this is going to be 2, 4, 6. I have 2 electrons left over. Now, normally I put those 2 electrons that are left over on the terminal atoms. Terminal atoms terminate the chain or the outer atoms. And so normally I'll put those on these atoms here, but hydrogen can't accommodate more because the max hydrogen can accommodate are 2, and then that fills up its shell, the first shell. And so the extra 2 electrons have to go on nitrogen. Well, it turns out that's a good thing because we want the extra electrons to go on nitrogen. All right, so once we get the skeleton and we've used up 8 electrons, this is 8 electrons here, that checks out with this. We check the octet rule. Does hydrogen have an octet? No. So this doesn't have an octet, but for hydrogen we have to use the duet rule rather than the octet rule. And so that's okay. Because hydrogen's in the first shell and we only need 2 electrons to fill the first shell, and each of these hydrogens has that. So it's a filled shell configuration with 2 electrons. How about nitrogen? Does nitrogen have a octet? Yeah, nitrogen has an octet. It's 8 electrons. This is an octet. So we want to make sure the octet and duet rule are satisfied, and they are in this case. There are 3 ways. Did I talk about the 4 ways of counting electrons? No? Okay. The 4th way isn't exactly counting, but close. One is octet and duet. Two is formal charge. The formal charge is equal to the charge on an atom assuming 100% covalent bond. That is, a 100% covalent bond, it means that there's 50-50 sharing. 50-50 sharing is just even sharing. The third way is by oxidation state. The oxidation state is the charge on an atom, assuming. Do you know what the opposite of a covalent bond is? An ionic bond. It's where we don't share at all. Covalent bond is even sharing. Ionic bond is winner takes all. And so the oxidation state is a charge on an atom assuming we have 100% ionic bonds. If we have 100% ionic bonds, that means it's 0% covalent. There's no sharing. And so we say that winner takes all. The fourth way is some compromise between the two extremes. You'll have to give my computer a moment. Well, let's take a break now, and then we'll start up after the break. My computer's hung up. So we'll go for a 15-minute break or so. Hopefully after that, this thing comes back. All right. The other way of counting electrons is something in between the two extremes. And the two extremes are going to be number 3 and number 4. And so let's take a look at that now. So somewhere between, or something between the two extremes. And 3. If we're at the extreme 2, for example, we have 100% covalent. Which is 0% ionic. And so on one side of the extreme, we have this here. At the other side of the extreme, we have 0% covalent, 100% ionic. And so it's not always black and white. So for example, this might be white here. This is black here. It's going to be somewhere in the gray region. And so here we'll just have this as a gray region. So if it's somewhere in the gray region, it might be like 60% covalent, or 40% covalent, or 40% ionic, something like that. It's somewhere here. And that's going to give it what we call a partial charge. And so over here we have 0 charge, over here we have a full charge, over here we have partial charge. Partial charge, where we use deltas to represent the partial charges. And so this is the delta plus, delta minus region here. And so that's yet another way of counting electrons. So if we were to look at a quick example here, something like HCl, chlorine doesn't have enough strength to completely take the electron from hydrogen, so there's going to be a bit of a tug of war. But if we do formal charge, I'll do formal charge as circled charges here. So if we look at HCl, well, this would be the Lewis structure for HCl, and the formal charges are going to be 0. If I do the oxidation states, the oxidation state is +1 for hydrogen and -1 for chlorine. But it's not 100% covalent because chlorine is more electronegative than hydrogen. But then again, it's not 100% ionic because chlorine doesn't have enough strength to completely strip the electron off hydrogen. And so what results is a charge on chlorine that's between 0 and -1. I don't know exactly what that is, but we could use quantum mechanics to figure it out. But we're just going to call it delta minus. Delta means it's somewhere in between 0 and -1. And over here, the charge on hydrogen is somewhere between 0 and +1, so we call that delta plus. And so it's somewhere in between the two extremes. And so that's the fourth way of counting electrons. In this sense, number 4 is not really counting electrons. It's just saying how the electrons are distributed in the structure by using the electron counts that we did earlier. So when we do Lewis structures, so for example, ammonia, NH3, I'm going to do that one here. We're going to do this in these steps. The first step is to total up the number of electrons. There are shortcuts you can do, but it's best to learn the long way before taking all the shortcuts. How many valence electrons does nitrogen have? Did we already do ammonia? No, all right. Yeah, this is 5 electrons, and then the hydrogens, and then the skeleton. We did that? Yeah, I guess we just did that. This is dementia setting in, unfortunately, early onset. But what we didn't do is the formal charge, correct? Or did we do the formal charge too? We did the duet and the octet, but did we do the formal charge? No, we did not. So we're going to do the formal charge. Now the formal charge is we're going to share the bonding electrons evenly. And so if I look at these bonding electrons here, this line consists of 2 electrons. And so what we're going to do is we're going to give one to hydrogen, the other to nitrogen. So it's just a fair split. And I'm going to have to do this because nitrogen had 5 valence electrons, and then we had 3 hydrogens, which is 3 times 1 valence electron. And that gave us a total of 8 electrons for this structure. Now, when we count the electrons, how many electrons does hydrogen end up with here? It ends up with 1 electron. Okay. Now, what I do is I compare. Hydrogen ends up with 1 electron, and how many did it donate to the structure? It donated 1 electron. Another way of thinking about this is, you know, the state of California, they complain because the state of California complains about the federal government because the state sends a lot more money to the federal government than they get in return. So let's say for every $100 they send to Washington, D.C., only like, let's say $80 makes it back to California. And so that's one of the complaints. I don't know what it is, the numbers. And then other states, for every $100 they give to the Washington, D.C., they get more than $100 back. Maybe they get $120 back. Well, in this case, this is fair. Hydrogen donated 1 of its valence electrons to this Lewis structure, and then when we look at the structure itself, it still has 1 electron. And so what we say is this. The formal charge is equal to the number of electrons that it got in the structure minus the number of valence electrons. So formal charge equals number of electrons minus number of valence electrons.
What's the difference between formal charge and oxidation state?
I'll talk about that in a second. So in this case, it has one electron in the structure and it gave one. So 1 minus 1, the formal charge is 0. Now zero formal charges aren't normally written, just the non-zero ones, but I'm going to write it. And when we write formal charges, I'm going to circle them. It's not a law that you have to circle them, but by convention, most people just circle it. How about these two? Are these two split, the 2 electrons in the lone pair? No, there's nobody to split them with, so those 2 electrons belong entirely to nitrogen. However, these bonding electrons are split, one to nitrogen, the other to hydrogen, and these bonding electrons are split, one to nitrogen, one to hydrogen. And so if I look at all the hydrogens, they all end up with 1 electron. If hydrogen ends up with 1 electron and it donated 1 electron to the structure, then the formal charge is 0. How many electrons does nitrogen end up with? So we count them 1, 2, 3, 4, 5. So nitrogen ends up with 5 electrons. How many did it donate to the structure? 5. So it gave 5, it ends up with 5. That means it broke even. It's 0. It's neither deficit or an extra. And so the formal charge is all 0. Now, for oxidation states, we count that differently. We'll split up the electrons differently. And so how would we do this using oxidation states? So this is for formal charge here. For oxidation state, which I'm just going to call OS for oxidation state, we assume that the bonding is not 100% covalent. We assume the opposite. We assume that it's 100% ionic. And what that means is winner takes all. But which atom is going to win the tug of war? The more electronegative or the less electronegative? In a tug of war for electrons, which one wins? The more electronegative or the less electronegative? The more electronegative. And so which one's more electronegative, hydrogen or nitrogen? Nitrogen. And so what that means is nitrogen takes both of these. And both of those. And both of these. And then it has these 2 that already belong to it. And so that means hydrogen ends up with no electrons. So hydrogen ends up with 0 electrons. How many electrons did hydrogen contribute to this? 1. And it ends up with 0. That means it's lost an electron. If you lose an electron, do you become increasingly positive or do you become increasingly negative? Positive. So the oxidation state here is +1. Now for oxidation states, we put those in parentheses like this. And if it's +1, we write the 1. So all these hydrogens are in the same boat. They basically have no electrons, and they're all +1. How many electrons did nitrogen end up with? 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen ends up with 8 electrons. And how many did it contribute? It only contributed 5, but ends up with 8 electrons. That means it's gotten 3 extra electrons. If it has 3 extra electrons, that's 3 extra negative charges, which means the oxidation state of nitrogen will be -3. So oxidation state is most important for redox properties. So this gives us 2 contrasting numbers. Is nitrogen 0 or is nitrogen -3? And the thing is, we never compare the 2. Because, did I mention apples and oranges already? No? Yes?
Yes.
Yes?
We're talking about reductors and oxidants.
Okay, yeah. Well, I'm going to use apples and oranges for another analogy here. The other analogy is this. When we look at oxidation states, we only compare oxidation states with other oxidation states. We never compare oxidation states with formal charges. It wouldn't make sense. So we compare formal charges versus other formal charges, and we compare oxidation states with other oxidation states, but we never cross-compare. It makes no sense to cross-compare. And they're both useful, even though they're both at the extreme, they're very, very useful numbers to have. Of course, it would be nice to have the numbers from quantum mechanics, but the numbers from quantum mechanics are going to require a computer. This, we don't need a computer to do this. We can just figure it out based on this. So for oxidation states, we use these primarily for redox properties, and we compare redox properties between different substances. Over here for formal charges, we use these for Lewis structures and acid-base behavior. Secondarily, we could use oxidation state for acid-base behavior as well. And so plus acid-base. But it isn't its primary use. For oxidation state, primary use is for redox properties. So when we do Lewis structures, we always do formal charges. And so for Lewis structures, we generate the Lewis structure following the steps. And we look for two things. The first one is going to be octet, duet. And the second one will be formal charge. We want to look at the formal charges. Why? Because the formal charges will tell us something about stability. And so let's say if somebody donated 5 electrons but got no electrons back, they might think it's quite unfair, like nitrogen, and it might be unhappy because of that.
Is the number of electrons in the structure for formal charge minus the number of valence electrons? Is it 8 or is it?
No. Number of valence electrons is off the periodic table. How many valence electrons does nitrogen have normally? 5. Oxidation state is the exact same equation.
What's the number of electrons in the structure?
How we just counted here.
Is it 8?
In this one?
Yeah.
No, it's 5. 1, 2, 3, 4, 5. Oxidation state is equal to the number of electrons in the structure minus the number of valence electrons. Exact same equation, but a different number. Exact same equation, but different number. Over here, how many electrons in the structure? 1, 2, 3, 4, 5. Over here, how many electrons in the structure? Actually, I got it backwards. Shoot. I have to adjust this. Let me flip it. Actually, let me just rewrite it. I'll just rewrite it down here. The formal charge is equal to the number of valence electrons minus the number of electrons in structure. So for nitrogen, the number of valence electrons is 5 minus 5 in the structure is 0. For oxidation state, it's the number of valence electrons minus the number of electrons in the structure. Number of valence electrons is 5. How many electrons in the structure for this? 8. 1, 2, 3, 4, 5, 6, 7, 8. So 5 minus 8 gives us -3. In reality, the charge is not 0 and the charge is not -3. In reality, the charge is somewhere in between the two extremes. But in order to figure that out, we need a computer. We don't want to deal with a computer. And so we're just going to look at things via the extreme. So when we're doing Lewis structures, we do formal charges. We don't have to do oxidation state. Do not have to do oxidation state. All right, are you ready to try one here? For practice, not a quiz. Hopefully this does not hang up again. Let's try this one, NH4 plus. How many electrons did you guys get? 9? Okay, let's count it up here. So nitrogen has 5 electrons, and then we have 4 hydrogens, and that's going to be 4 times 1 electron, except there's this positive charge here. What do we do about a positive charge? This positive charge means we lost an electron or gained an electron? We lost. And so we have to account for that lost electron here. It's going to be -1 electron because of this plus charge. Oops, actually, I offset this. Let me redo that. Here. So the +1 charge means -1 electron. So it's opposite, so it's kind of funny. So what we end up with is not 9 electrons. What we end up with is 8 electrons. Now, hydrogens, like fluorine, can only be terminal. And so we can't have hydrogen in the center of anything. So what we do is we'll put nitrogen in the center and then attach all the hydrogens to it. And then take a look at how many electrons did we use up. 8. Okay, then what do we do next? So this structure is going to have 8 electrons. That checks with this. 8 electrons. That's good. What do we do next? We look for the octet and the duets. So nitrogen has an octet, that's good. Hydrogen, we can't get an octet anyway because it's in the first shell. We only end up with a duet. And so this looks good. 2 electrons for the duet, 8 electrons for the octet. All the hydrogens have a duet and the nitrogen has an octet. And so that's good. All right, the next way we count this is we look for a formal charge. How do we split the bonds when we have formal charge considerations? We split the bonds right down the center. And then count them. Each bond consists of 2 electrons, 2 dots. And so that means hydrogen ends up with how many electrons here? 1 electron. And how many did it donate? 1. So it broke even, and therefore the formal charge is 0. All the hydrogens are the same. They all end up with 1 electron, and they all have a formal charge of 0. How many electrons did nitrogen end up with? 4 electrons. How many did nitrogen donate to the structure? 5. So nitrogen ends up losing or gaining an electron? Losing an electron. If nitrogen loses an electron, then what is its formal charge? +1. Like that. It's going to end up with a positive charge because of that. And so finally, what we can do is we just write the structure over here. The 0 formal charges aren't usually shown, just the non-zero formal charges. Now with oxidation state, we'll write it +1, but with formal charge, we'll just write the plus symbol in there, and that represents +1. The other thing we often do is we write the net charge using square brackets. And so the net charge on this is plus due to the positive formal charge here. And so the way we read this is +1 plus 0 plus 0 plus 0 plus 0 gives us a net charge of +1. And so that's the net charge on the outside of the bracket here. This is net charge, which is equal to the sum of the formal charges. And this would be the formal charge here inside the bracket. So either this top structure here or the bottom structure is fine for the final answer. The final answer would be this would be the little structure here or here with the brackets. Okay, the next one we're going to do is this one here. The amide ion or the amide ion. So give this one now. How many electrons did you get? 8. 8 is correct. 5 electrons from nitrogen, and then 2 times 1 electron from hydrogen, and then we have a -1 charge, which means +1 electron. It gives us 8 electrons. And then you probably put it in the center like this. But how many electrons have we used up here? Each line represents 2, so this is only 4 electrons. And I have 8 electrons here, so where should I put the remaining electrons? Normally the remaining electrons go on what we call the terminal atoms. Hydrogen would be the terminal atoms, but hydrogen can only accommodate a duet. And so we aren't going to put them on hydrogen. We're going to have to put them on nitrogen. Well, it's good we put them on nitrogen because nitrogen needs an octet, and it didn't have an octet before, but now it does have an octet. And so let's go ahead and take a look. Hydrogen has a duet, and nitrogen has an octet. So we're good with the octet rule and duet. All right, what's the next thing we do? We do formal charge. So when I do formal charge, I look at splitting the bonding electrons in half, like so. That means nitrogen ends up with how many electrons here? 6 electrons. And hydrogen ends up with 1 electron each. So hydrogen got 1 electron in the structure but contributed only 1 electron, so it broke even. But what about nitrogen? Yeah, nitrogen ends up with 6 electrons, but how many did it donate to the structure? 5. So it ends up with an extra electron, which means has a negative formal charge.
The electron coming from isn't just like free floating out there?
It's from somewhere. It took it from somewhere. Not from the hydrogens, but it took it from something else. And so what we end up with is this. We don't show the zeros, but we will show the negative formal charge like that. Or we can use these square brackets. Like so.
You have to show the electrons when it's used for
Yeah, you should. In organic chemistry, they don't show the electron as dots here. They don't even write the lone pairs here. But that's a shortcut, you know. You should learn the long way before taking any shortcuts. All right, there's a pattern here. If nitrogen has no formal charge, how many bonds does it make? If nitrogen has no formal charge, how many bonds? Not 2. Not 0. Well, let's make it easier. If nitrogen has a -1 formal charge, how many bonds do you see? 2. 2 bonds. If nitrogen has a positive formal charge, how many bonds do you see? 4. And if nitrogen has no formal charge, how many bonds do you see? 3. This pattern repeats itself for other elements as well, but the numbers are different. So for example, when oxygen has no formal charge, it forms 2 bonds. When it has a negative formal charge, it forms 1 bond. When it has a positive formal charge, it forms 3 bonds. And so that gives you some additional clues as to what to do. All right, when we do Lewis structures, this totally ignores the 3-dimensional shape of it. When we do 3-dimensional shapes, we look at something called valence shell electron pair repulsion, or VESPR. In other words, these electrons, or these groups of electrons, will try to maximize the distance from one another because they repel each other. And so we have something called electron pair geometry, electron pair angle, etc. I don't like to call it pairs because sometimes they're more than just pairs. So if I have 2 groups of electrons, let's say like 2 bonds like this, in order to get the electrons as far apart from each other, we want to adopt a 180 angle here between them. If we have 3 groups of electrons, these 3 groups want as much space from each other as possible. And so we have to arrange these at 120-degree angles like this. When we have 4 groups, then the maximum distance between these is if I arrange it in this type of structure, like this. All the angles are 109.5. And so we maximize what we say is the breathing room or distance between those groups. And we have names for this. This is called linear. This one's called trigonoplanar. And this one's called tetrahedral. Tetrahedral is like a sphere. It's like a ball. each of those legs is the exact same as the others, so we don't have legs and arms. They're all legs. We can see this with balloons. If I have two balloons, then to get the maximum distance between the two balloons, we'll want to adopt a 180 angle, and we call that linear. If I put in three balloons, then the maximum angle between the three balloons will be 120 degrees, and we call that trigonal planar. If I put a fourth balloon, that's going to push the other three down. So this is with four balloons. And the angle is, in three dimensions, 109.5 degrees. It's called the tetrahedral angle, and the shape is called tetrahedral. This is like a ball, a spherical shape. No matter which one of these balloons you grab, it looks exactly like the other. And so this is what we call spherical symmetry. There's no top, there's no bottom. It's just four-legged ball is what we have. And so we're going to be looking at the geometries, but before we do the geometries, we want to make sure we master Lewis structures first. And so that's what we're going to do, and then we'll look at the geometries, which is the second step after generating the correct Lewis structure. And so we're looking at ammonia here. Let me insert some slides. Oh, this is working here. It's not working here for some reason. Shoot. Oh, too many things open, probably. All right, it looks like Microsoft Word is working, so let's just switch over to Microsoft Word. And we're going to take a look at some ones from the lab that we're going to be doing. This is the next experiment that we're going to do, and this is experiment 8. So let's take a look here. Oops, went too far. Go back to experiment 8. 1, 2, 7. Lewis structures and molecular geometry. So we're going to focus on this part, the Lewis structures, and then later on we'll look at the molecular geometry. So we did ammonia. Okay, the next one we're going to do is PCl4+. PCl4+. You don't need to know the name for this. It's a polyatomic cation. Did you get 32 electrons? All right, there's another rule that we use, and that is we place the least electronegative atom in the center. And so phosphorus versus chlorine, what's more electronegative, what's less electronegative? Which one's the least electronegative? Phosphorus. The further to the left and the more down it is in the periodic table, the less electronegative it is. And so we'll throw phosphorus in the center and bond that to all the chlorines here. If we do this, how many electrons have we used? 8 out of the 32. And so what we try to do is we try to complete the octets to the more electronegative elements first, which would be chlorine. And so that would require 3 lone pairs on each chlorine, like so. And then phosphorus already has an octet, so I don't need any more electrons for that. But how many electrons have I used up now? 32. So that's correct. It's 32 electrons. So that's checked. Okay, what do I do next? I do the formal charge. Formal charge we could box. I'm just going to box this here. I split the bonding electrons in half. Lone pair electrons just belong to whatever atom they're attached to. So all those lone pair electrons on chlorine belong only to chlorine. They aren't shared with phosphorus. And so the chlorine ends up with 2, 4, 6 plus 1 from the bond, you know. And so chlorine ends up with 7 electrons. How many electrons did chlorine contribute? 7. So it broke even. So no complaints there. It's 0 formal charge on each of the chlorines. They're all the same. How about phosphorus? How many electrons does phosphorus end up with? Phosphorus only ends up with 4. How many did phosphorus contribute? 5. And therefore its formal charge will be plus 1. And so when we draw the Lewis structure, we draw the structure plus any non-zero formal charges. Mm-hmm.
Can you say that the trend is like the further you go to the right and down, it's more electronegative?
And up. The further right you go and up, it's more electronegative.
So if it was phosphorus and nitrogen for some reason, that means that phosphorus would be in the center.
Yep. Yeah. All right, so this would be the structure. Or we might see it like this. With the square brackets. And the net charge. The net charge is pretty much the same as this charge on this phosphorus. Or we just don't even bother writing the formal charge and we just write the net charge. Like this. Where we'd have to figure out where that positive charge is. Or how that net charge comes about, because the net charge is the sum of all the formal charges. All right. That's that. Then let's take a look at the next one, NOCl. NOCl. All right, why don't you give NOCl, but N has how many valence electrons? O, Cl,
7,
and so that gives us how many? 18 electrons. All right, which atom should I put in the center? Nitrogen or oxygen? It looks like oxygen. Oxygen goes in the center of a lot of things. So we see oxygen is in the center of water. And so maybe we'll just put oxygen in the center between the nitrogen and the chlorine. But that violates that rule. What was that rule? Least electronegative. If I put the least electronegative, it should be which one? Nitrogen or chlorine? We'll just throw the nitrogen. Chlorine doesn't like to be in the center of anything. Nitrogen can be, like in ammonia. And so we'll just throw the nitrogen in the center. And so we have option A or option B. All right, now we have 18 electrons. I've used 4. And then I'm going to complete the octets. So what I'm going to do is I'm going to complete the octet to the nitrogen. Nitrogen's smaller. So let's go ahead and do that. And then the chlorine. And so we usually complete the octets to the, what we call the terminal atoms here first. All right. And now how many electrons have we used up?
There's 6 electrons in it?
You're not going to use the right side.
I am.
The right, along with the nitrogen.
We'll do that one. We're going to do both. So how many electrons have I used up? 2, 4, 6, 8, 10, 12, 14, 16. How many do I have? 18. So I have 2 extras. The 2 extras I'm going to put in the middle, which we call the central atom. But we have a problem here. The problem is nitrogen has an octet. That's fine. Chlorine has an octet. That's good too. But what about oxygen? Does oxygen have an octet? No. Oxygen's only at, no, not 8 electrons. How many electrons does oxygen have? 6. So let's write that. But I've ran out of electrons. I don't have any more electrons I can put on nitrogen, or not nitrogen, on oxygen. And so we have this option of making a double bond. And so if I convert one of the lone pairs into a bonding pair, then I can form a double bond and then donate some of the electron density to oxygen. And so which one do you think is more likely to form more bonds, the nitrogen or chlorine? It turns out it's nitrogen. It's capable. We could do it the other way too with chlorine and see what happens. But we end up with this. As one option. Or, let's call this option 1. Or if we did it with chlorine, we'd get option 2. So let's take a look at what that looks like. If I did it with chlorine, I'd have nitrogen with 3 lone pairs, single bonded to an oxygen, 1 lone pair, and then this would be double bonded to the chlorine. Either way is going to satisfy the octet rule because nitrogen now has 8 electrons. Oxygen now has 8 electrons. And chlorine now has 8 electrons. So everybody has an octet. What about this structure here? Does everybody have an octet? Yeah, everybody has an octet. And so both of these structures satisfy the octet rule. Although both of those structures satisfy the octet rule, we don't just look at the octet rule. What else do we look at? We look at formal charge. So let's count up the formal charge by splitting the bonding electrons down the middle. How many electrons does nitrogen end up with in the structure? 6. How many did it contribute? 5. So it ends up with an extra electron. We give it a minus formal charge, extra electron. How about this oxygen? How many electrons does this oxygen end up with? Not 6. 5. It ends up with 5. How many did it contribute? 6. So it lost an electron. It's positive. Chlorine. How many did it contribute? And therefore it's 0. And so one way of visualizing what's going on here is that oxygen lost an electron to nitrogen. Does that seem to make sense? Which one is more electronegative, oxygen or nitrogen? If there's a tug of war, which is stronger, the oxygen or the nitrogen? Oxygen. So does this look like a favorable outcome? No, this doesn't. How about this one here? Let's take a look at the formal charges on this next structure here. All right, how many electrons does nitrogen end up with in the structure? 2, 4, 6, 7. 7 electrons. How many did it contribute? 5. So it came out with 2 extra electrons, which means its formal charge is minus 2. Okay, this oxygen? 5 electrons. It contributed 6, therefore it lost 1. Plus 1. How about this chlorine? It ends up with 6 electrons. And how many did it contribute? 7. And therefore it lost 1 electron. 1 negative charge giving it a positive charge. So the way I read this is that nitrogen is in a tug of war with oxygen and chlorine and manages to take an electron from oxygen and take an electron from chlorine. Does that look likely? This looks even worse, right, than this one. So if you're going to pick one of these, I'd probably pick the one with fewer formal charges like this one here. But we also have an option though, and the formula, the way the formula is written, we don't have to bond that way, because if you look at the formula, it looks like the oxygen is in the center, but it doesn't have to be. And in this case, oxygen is not in the center. Oxygen is actually on the periphery, and nitrogen's in the center. So let's go ahead and finish this structure here. So I'm going to complete the octet to the most electronegative element, which would be oxygen first. So here, now oxygen has an octet. Then I'm going to go to chlorine. We do the terminal atoms first, and then any remaining electrons we put on the central atom here, like this. Now I have a choice. Again, I could have oxygen donate because nitrogen doesn't have a octet, or I can have chlorine donate. In this case, What do you think? On the one hand, chlorine, because chlorine's less electronegative. On the other hand, oxygen, because oxygen likes to form how many bonds usually? If you think of water, how many bonds does oxygen form? 2. And so, on the other hand, it seems like option 1's better. Because the halogens don't like to form more than one bond. They can, but they don't like to. And so, let's take a look at option 1 here. See what the structure comes out to. And so, if I were to form a double bond, that is convert a lone pair into a bonding pair, it's going to look like this. And so this is the end result of option 1. Okay, now let's look at the formal charges here. And so I'm going to split the bonding electrons down the middle and then count. How many electrons does oxygen end up with here? 1, 2, 3, 4. The lone pair belong entirely to it, and then half of the double bond. 6. How many did it contribute? 6. So the formal charge is 0. Okay, let's go on to nitrogen. How many electrons does nitrogen have in the structure? 5. How many did it contribute? 5. It ends up with 0 formal charge. And then we go on to this chlorine. Chlorine has how many in the structure? And it contributed 7, so 0. So that's good. It's like if you give $100 to the Washington, D.C. and you get $100 back, you can't complain. Right? That's good. How about if we chose option 2? If we chose option 2, what would we have ended up with? And so I'm going to form the double bond now with the chlorine. I forgot to do the octets, but you can see the octets are fine. We have an octet around oxygen, an octet around nitrogen, and an octet around chlorine. The octet rule is fine here. Octet around oxygen, octet around nitrogen, and an octet around chlorine. Oh, wait a minute. Is that an octet around chlorine? No, it's more than an octet. It's more than an octet because I forgot to erase the lone pair here. Okay, now it's an octet. All right, so let's do formal charge next. All right, around this oxygen, how many electrons does this oxygen have? 7. It contributed 6. Therefore, as an extra electron, giving it what formal charge? Negative. Okay, this nitrogen ends up with five. It contributed 5, and so formal charge 0. This chlorine 6. It contributed 7, so its formal charge is going to be +1. Out of these 4 structures, which one do you like the best? Yeah, the third one. So this is the correct structure here. This third one. And so the way we'd write it is this. There's no formal charges. And the bonding looks normal. If there are no formal charges, we don't write anything. There. So that would be it.
But even with the other ones, the no charge still comes out to look like the...
Yeah. if net charge comes out to 0, then we don't have to write it there, but it's helpful to write it though, regardless. For all of these, it helps. Okay, that was this, nitrosyl. Let's do this one, the nitrite ion. NO2 minus. Actually, I'm getting tight on time, so we'll do this together. Nitrogen has 5 electrons, and we have 2 oxygens. Each oxygen 6 electrons. And then we have a -1 charge, which means we have to add an additional 1 electron per charge. And so this is going to be 12, 17, 18. This is also going to be 18 electrons. Now, what do we want to put in the center? Do we want to put nitrogen in the center or oxygen in the center? We're going to put nitrogen in the center. And so this is going to be O and O. We don't want to put oxygen in the center because what can result is this. This bond here, the oxygen-oxygen single bond, is called a peroxide bond. Peroxide bonds are unstable. Inherently unstable, and we try to avoid these if possible. But sometimes it's not possible because the compound itself is a peroxide. And so that's another reason I'm going to put nitrogen in the center. Okay, then I have 18 electrons. I've used 2, 4. I've used 4 of them. So what we do is we try to complete the octets to the peripheral or terminal atoms. And so this is 2, 4, 6, 8. 8 times 2 is 16. I've used 16, and that leaves me with 2 electrons left over. So do I have an octet around nitrogen? No. But I don't have any more electrons. I've used up all my electrons, and there are no more electrons to use. And so what I'm going to have to do is I'm going to have to make a double bond. That is, convert a lone pair into a bonding pair. But I have 2 choices here. I could do it from the left oxygen, or I could do it from the right oxygen. Okay, so let's choose path 1. We're going to do it from the left oxygen. If I convert a lone pair into a bonding pair, I'm going to be left with 2 lone pairs rather than 3 lone pairs. And I'm going to form a double bond rather than a single bond. And so I have something like this. So when I look at this, I have a octet. I have an octet, and I have an octet. And so the octet rule is good. The next thing I look at is formal charge. What's the formal charge on this oxygen? Can you just look at it and see the formal charge, or not? So when I look at this oxygen, I see 1, 2, 3, 4, and then I have to visualize splitting these in half. And so it'd be 1, 2, 3, 4, 5, 6, 0. 0 we don't need to write. This nitrogen, 1, 2, 3, 4, 5. Its formal charge will be 0. This oxygen?
7.
Yes, 7, and therefore it's going to get a minus charge here. So this nitrogen has a formal charge of -1. Here, we can do it the same color. What if we picked path 2? If we pick path 2, then we're going to form this. We're going to form the double bond on the opposite side. Take a look at the first oxygen. What's the formal charge on this first oxygen? It ends up with 7 electrons. 1, 2, 3, 4, 5, 6, 7. It donated 6. Therefore, this is going to be minus. Nitrogen, 0. Oxygen, 0. Okay, so which one do you prefer? Structure 1 or structure 2? Which one do you prefer? Which one's more stable? It looks the same, right? It's the same, but it's different. It's the same because if you just flip this, just take this ion and just flip it 180 like that, and then they're the same thing. But they're different because we had a choice, and we could have done it the left, or we could have done it the right. And so when we have a choice like that, both tend to happen, and what we end up with are both of these structures. We call these resonance structures here, and we show this with arrows. We form these resonance structures when we get a choice, like this, and we go down one of two equivalent paths. So that would be it. And so there are 2 resonance structures here. One where we put the double bond on the left, the other where we put the double bond on the right. Now, resonance, people usually think of some kind of oscillation. And when we think about it, the double bonds are shorter, single bonds are longer. Double bonds are stronger, single bonds are weaker. And so a lot of people think that this goes double, single, and it just oscillates. And regarding length, it would be short, long, short, long, short, long. Well, the single bond would go single, double, so it would go long, short, etc. And so they think that this thing is oscillating, but it turns out that it doesn't oscillate. There's no resonating here. What's happening here is this is a failure of valence bond theory. There was another failure of valence bond theory. Did I talk about it? Oxygen. Oxygen, we need MO theory. O2 is a failure of valence bond. This is not accurate. Even though this is the way we draw the Lewis structure, it's not accurate. And so what we do is we do a modification of this. It turns out both bonds are equal.
So resonance structures are favored for
Hmm?
valence bond.
Yeah. And so to get it more towards what it should be, then what we do is we come up with a hybrid structure. A hybrid structure would be more in line with MO theory. A hybrid structure for this shows that both oxygen-nitrogen bonds are equivalent. So we end up with some kind of structure like this. Rather than going from double bond, single bond, double bond, single bond, like that, and oscillating, it's just one bond. And both of these bonds are exactly the same through experimental measurement. And so the valence bond predicts these bonds are going to be different lengths. Experiment shows both of these bonds are exactly the same, so Lins is experimental fact twin, and so the theory had to be modified. And so the way they modified valence bond theory was coming up with something called the hybrid structure. The hybrid is a hybrid of these two. And the hybrid is just kind of the average of these two structures, and that would be this, in which both of the bonds are the same. So rather than being double single, it's what we call 1.5 bond, or a dashed up line. And rather than single double, it's a 1.5 bond. So both of these bonds are exactly the same, at 1.5. And so it turns out that for resonance, we use the double-headed arrow here, and then we draw both structures here. And so the final answer would be this, the two resonance forms. Okay. Let's move on to HNO2. Okay, the next rule is this. I'm a little bit behind, but that's all right. The rule is acidic hydrogens bond to the most electronegative atom or atoms. And so when I look at the formula, it looks like the hydrogen is bonded to the nitrogen. No, that turns out to be wrong because in this acid, the hydrogen is actually bonded to the oxygen. But you can't rely too heavily on the formula to tell you how it's structured. And so let's go through this one quickly here. Hydrogen has 1, nitrogen has 5, and then we have 2 oxygens. This would be 2 times 6. And altogether, we're going to have 18 electrons, once again. Which atom are we going to put in the center? Hydrogen cannot go in the center. And so the hydrogen, the hydrogen is acidic, so it's going to bond to not nitrogen, it's going to bond to oxygen. And then what we're going to do is we're going to throw nitrogen in the center here, like this, and throw the other oxygen out over there. Now, I've used up how many electrons? 6. And so what we do is we complete the octet to the terminal most electronegative. And so the terminal most electronegative would be this oxygen here. And it needs 6 more electrons to complete its octet. So that's complete. Then we do the next most electronegative, which would be this oxygen here. The 2 oxygens should be the same, but the terminal goes first. And then we do something called the bridging oxygen. This is the bridging oxygen here. And so far we've used up 2, 4, 6, 8, 10, 12, 14, 16. And that leaves us with 2 more electrons here, like that. And we'll throw those on nitrogen. But when we look at nitrogen, does nitrogen have an octet? No. And so in order to make an octet, we run out of electrons because we've used up all 18 electrons. And so we can't add more electrons. And what we're going to have to do is we're going to have an oxygen sacrifice some of its electron density. And so this is option 1. This is option 2. Should we have the left oxygen donate or the right oxygen donate? Or does it make a difference? And so if we go down the path for option 1, we end up with this structure here. If we go down the path of option 2, we end up with this structure here. Which one do you prefer? Option 1 or option 2? Both of them have an octet on all atoms, except for hydrogen, which is a duet. But think about it. We're out of time, so we're going to continue this on Monday.
So is the exams going to be chapter
10 through 13.
So not 14 yet?
No 14. And I haven't covered the structure part of 13 yet. I'll cover that on Monday.
Can I turn this in? And then also, I was just looking at like my old notes, and I was wondering if this would be okay to study, or if you kind of refer to it like differently.
Yeah,
That's good.
yeah, that's okay to study. All
Okay.
right.
All right. Thank you.
Thanks. Thanks.
Chlorine is more electronegative than nitrogen.
Fluorine?
Chlorine.
Chlorine? No, nitrogen is because it's smaller size, but as far as central atom, chlorine doesn't like, none of the halogens like to be central. Chlorine can be, but you know, they don't like it.
It's kind of confusing because, like, well, technically it's lower
Yeah, I mean, it's all kind of
general.
confusing, yeah, unfortunately.
I have a club meeting tomorrow.
Okay.
So
Yeah, no, I don't expect you to do don't worry about it.
You know, like, it just happens every 2 weeks.
Yeah. Yeah, actually, I'm probably going to miss tomorrow's meeting anyway, so that's good. But thanks
Do
for,
they penalize you?
they might, depending on the hours.
Depending on the hour.